then we will get this show on the road. Talking about binomial coefficients. You did not have to be here 12 hours ago to understand what a binomial coefficient. If you weren't here 12 hours ago, shame on you. But we'll talk about it again anyhow. And once Anna comes back, I will definitely start. But because, are we good? We're good, okay, so we are gonna start. So binomial coefficient, just to get the ball rolling, what the heck is that? Why does this intro slide make sense? Well, binomial coefficient, and I mean it makes sense numerically, and that's about it, but that's okay. What is it? There you are. Got to have that I there. So the binomial coefficient, n choose k. Let's write that, how we read it, because it's a weird symbol. N choose k, but the way we read it is exactly how we're trying to describe it. We are counting how many ways there are to choose k things from an n set. So, for instance, we know, and also, I think let's just write it here. We also know a numerical value for n choose k. It's the same as n factorial divided by k factorial times n minus k factorial. I don't believe this will really pop up. It might pop up near the end of this section, but for the most part, you can kind of figure things out in other ways. But let's actually see what we got here. What kind of problem do we got? Yes. So earlier, we were sort of using binomial coefficients to do counting problems. Now we want to prove some things about the binomial coefficient. Okay, we have this thing, it's called the chairperson identity. It says n times n minus 1 choose k minus 1 equals k times n choose k. Okay, why we call this the chairperson identity? Why is it an identity? Let's find out. So let's first just write it up here on the board. Oop, there we go. And sort of see what the heck's going on here. Okay. So the idea about the chairperson identity is, imagine we have n a group of n people in a business. Let's say n people are in a business together. Sure. See, the thing is, though, if, there's n people in this business together, and we're gonna create this hierarchy where there's k of them that are going to be part of this select group. And one of those, how am I trying to say this? I think I'm saying this right. Let's just keep going. Yeah.
And a group of K with a chairperson.
Yes. Yes. A board of directors. I'm so bad when it comes to analogies. We're doing like a board of directors, and we have a chairperson on the board of directors.
Give us a way you would compare how you are with analogies.
I'm like no. Okay, so let's try and count this in two ways. If we can count this in two ways, then the two things are actually equal. This is that whole double count idea. So what's this left-hand side saying? Well, from these n people, I can choose one of them to be my chairperson. There are n ways. So let's just choose the chairperson right from the get-go. Awesome. Now we have this chairperson, so, but we want a group of k people. So from the n-1 remaining, we just fill out our board. Cool. Now, what else could we have done? Well, we could have instead simply chosen our board. So we're going to do this in a different order. We're going to do the n choose k first. We had n people. We're going to choose k of them to be our board. So pick our board. And now there's k people in our boardroom. We choose one of those k to be our chairperson. Perfect. Now basically this is telling us we can sort of choose the order in which we make this process, but at the end of the day, we get the same value, ergo, these two are equal. Wonderful. What else do we got here? Boom. Bow. Okay. So we talked about board of directors. Now we can talk about subcommittees. There's a theme here. I don't know if this theme will continue, but let's see. What do we got here? Now, instead of multiplying a number with a binomial coefficient and equating that to another number, actually, well, you know what? Maybe before I go on, let's actually maybe I should kind of examine this guy a little bit more. Why not? I have some time. Apologies, I'm sort of going free flow at this point. I got 1 hour of sleep between my last talk and now, and I've just sort of been around otherwise. So let's just sort of kind of look at this visually. It's kind of nice. You can kind of, if we take this k, kind of move it on over here, we get this sort of nice, interesting kind of look. It's kind of cute, where n choose k, you can just sort of subtract from both of your values here, and then just take them out as a fraction. A binomial coefficient is not a fraction. Don't get me wrong here, but there is this fun correspondence going on here. Now let's actually go on to our subcommittee identity. Now we have this product of binomial coefficients equaling another product of binomial coefficients. What we got here? We got n choose k times k choose r equaling n choose r, boop, 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 times n minus r choose k minus r. So what do we think the scenario is here? What are we trying to do? What do we think?
Prove a binomial identity.
Ooh, very good, Van. Quick on your feet. Okay, so it's a subcommittee identity. Let's imagine we're trying to build a committee. Yeah.
So first, with the first n choose k, we choose the actual committee.
Okay.
And then with the k choose r, we choose how many committees we can make out of that committee. And by multiplying those two together, we find the total possible subcommittees, then I guess.
That's very, very close to like the way to describe it. Absolutely, you're right. So this is how many ways. So yeah, we're gonna choose a committee of k people. So let's actually write that down. So we're gonna choose a committee of k people. And then from that pool of k people, we're going to build this subcommittee. That's perfect. Let's build a subcommittee of size R. Right on. Okay, so that is how we go about it on this side. And now with our first example, or with the first identity, the idea was we pick the chairperson, pick the board after, or we pick the board first, pick the chair after. We're gonna do something pretty analogous here. I do know analogies. Okay, so instead, we're going to choose a subcommittee first. Our subcommittee is of size R, and there's N folks to choose between. So we choose R from our entire pool. So let's write that. Or we build that subcommittee of size R first. And we built the subcommittee, and we now want to build a committee around it. How many people have we, how many people can we choose from? Well, we picked R from N, so we have N minus R, many people remaining, and we wanted a committee of size K, so we're now gonna just choose K minus R, many people, to fill out our committee. And then, I guess finish your committee. Wonderful. With K minus R, other people. Oh my gosh.
Usually stops after a minute.
Yeah. I know this isn't the first time it's happened. I trust it'll survive the last 3/8 of this event. But yes. And so I guess I want to pause here and just sort of reflect. With binomial coefficients, there are actually like a vast array of identities that we can kind of build from them. This identity in particular, there are generalizations of it, and we can use these sorts of identities to, I guess, prove other identities along the way. We'll actually use, we might use one or both of these along the way. But, so these are two nice identities, but there's one identity that sort of has like top billing when it comes to binomial coefficient identities. And to sort of get there, we're gonna reintroduce this idea of a lattice path. So Van introduced this earlier. If you weren't here for those 6 hours, shame on you. But if you weren't here, let's just remind ourselves what a lattice path is. And in particular, a northeast lattice path. So what we're gonna do, and I'll actually just draw the picture here. Okay, so what we can do, we start with an integer lattice, and that just means we take a lattice, a grid, and we're just going to consider integer coordinates. And let's do this 5 by 5 case. Won't take too long to draw. Okay, yes. All right, and now what a northeast lattice path is that we are going to we're going to go from the point 0, 0 all the way up to some value let's say mn, in this case, why not 4, 5? And we can only get there by moves 1, 0 or 0, 1. A move 1, 0 is, we can think of it with cardinal directions, that's going east. We can think moving up or going to 0, 1 as a north direction, so a northeast lattice path. There are other types of lattice paths. Sometimes we can include diagonals, and you get some interesting sorts of patterns there, but it's a little beyond the scope of this. So we're gonna stick with these lattice paths. Now, why are these so nice? Well, we can actually use them to prove this identity right here. This is Pascal's identity. If you took algebra, you might have had to draw the first 10 rows of this, and you hated it. You didn't understand why. Why am I adding these numbers? Well, it turns out it's not only a triangle, but it's an identity. What's the triangle? We'll get there if you do not know what that is. But Pascal's identity, what's it say? It says that n choose k, that is, choosing k elements from a set of size n, is equivalent to the sum of n minus 1 choose k and n minus 1 choose k minus 1. That is, choosing k elements from an n minus 1 set or choosing k minus 1 elements from an n minus 1 set. So what the heck does that have to do with lattice paths? Let's look at this lattice, draw some paths between 0, 0 and maybe let's not go 4, 5. Let's go 3, 3. Okay, so if I'm gonna make a lattice path to 3, 3, then at every point, I guess, at the beginning, I have a choice. I go north, I go east. Maybe in this case, let's just erase this. I go north. Now, at this point, I can go east at most, I can go east 3 times still, and I can go north 2 times. So, I don't know, let's go north again. We go 0, 2. I can go north again, or I can go east, and if I go east, I can go east 2 more times. Let's just sort of fill out a path. Let's go east, east, north, and east. Okay, we went from 0, 0 to 3, 3, and we might ask ourselves, well, how many ways could I have actually done that? How many ways could I have done that? Well, as I was saying, at every point I can sort of decide, we can actually think about this from the get-go. I can, before I even start this, I can sort of envision I have to make 3 east moves and I have to make 3 north moves, right? I have to achieve a height of 3 and I have to achieve a distance of 3. So long as I do that in some particular order, may it be north, 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 east, 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 or north, east, north, north, east, east, et cetera, et cetera. Once I just have this path, it's sort of determined where I'm going to go. So, in this particular case, there are actually going to be, so let's write this, number of lattice paths from 0, 0 to 3, 3 is So we have 6 possible positions for, say, just our north moves. And we're just going to choose 3 of those positions. And once we do that, our east moves are actually locked in as well. So let's actually, I'll even change that up. We have 3 plus 3, choose 3. This 3 just being one of our moves, either our north or east moves, and then just summing up how many moves in total. So we can actually just kind of figure this out in general. If I want to go to, say, the point N, let me make sure I'm doing this one right. K minus, N minus, wait, oh, K, yes. Is that right? Yes. Thanks, John. Yes, absolutely. I might want to figure out the paths from 0, 0 to K, N minus K. That is, I have K north moves and N minus K east moves. So I have along that path, and let's just sort of basic setup again, number of lattice paths from 0 to 0 to K, N minus K. I have N total moves before I get to this point. That is N minus K plus K. And then I have K east moves. Wait, yes, I have K east moves. So I just choose where those positions are, and we have our number of lattice paths. Wonderful, and choose K. That's good. Now, why on earth is that also N minus K, N minus 1 choose K, plus N minus 1 choose K minus 1? Well, what if I just determined what my first move was? Say I know that I'm going to go east first. I'm still going to go from 0, 0 to K, N minus K, but I'm going to go east at the very beginning. So that means I have one less east move. So let's write that out. The number LP starting with E, move E. Okay, we can sort of do one of two things. Let's just sort of think of it like this. Let's fix that E right there, and then I have N minus 1 other spots here that I'm gonna fill. And I was filling them with my east moves. One of them's already fixed, so there are K minus 1, N minus 1, choose K minus 1 ways to figure out where our other east moves are gonna go. Now, awesome. If we don't start with an east move, we're just gonna start with a north move. So what the heck does that equal? I guess I'll move it over here. Just gonna be all around. I'll just point at the right things. If you trust me, we'll get there together. Okay. Okay, what if we start with a north move? Again, our pool of moves goes down to N minus 1, but we still have K east moves. Awesome. And every lattice path is going to start with an east move or a north move, and if I start with an east move, I'm not starting with a north move and vice versa. So these are mutually exclusive events, and they count up how many paths I have, as does n choose k. Ergo, I'll just put it up here. N choose k equals this whole thing. Perfect. Right on. Okay, how are we feeling? We're vibing? Righteous, okay. And if that proof wasn't convincing, before I get into that, actually, I forgot there was a little note. It's pretty cute, actually. Is that, if we think about it, this is actually a recurrence. It's a recurrence relation with two variables. The recurrences that Van worked with, I think he only ever worked with recurrences in one variable, like just an n.
Yeah, it's been so long.
I know. You're out of the fire now. So, but we can also just, we can have recurrences based around two variables, and Pascal's identity is one such event. Now, what do we have? So if counting lattice paths is not your thing, don't worry. I've got two other ways to prove this. If you were not convinced, maybe this will convince you. We'll see. Okay. Let's see. So part A here. What if instead we try and prove Pascal's identity by double counting subsets of size k from an n element set? Now we're going to do something kind of the same flavor as like subcommittee and chairperson identity, where we specify an element here. Now, this is my favorite element of the set from size n, and I'm going to take the sets that either include this element or don't. So let's write that down. So fix an element. Let's call it star. Fix an element in an n set. Have I used that?
It's like an n-gon.
It's like an n-gon. Yes. Fix an element in your set, and what we're going to do is we're just going to count the sets that contain this, or the sets of size k that contain this element, and the sets of size k that don't. And just from that similar reasoning in the last proof, those are the only two choices that we have. We either have this thing or we don't. So that will get us our count. But let's just start with, actually, I don't know how I want to write this. Am I big? I'm not big. Haha. Saved it. Okay. We got it. I don't know why, but just saying big and small it's very funny to me. And it's just about the screen. I just need to be, okay. Fix an element. All right. So what are we going to do? Let's count number of sets of size k. Sets size k containing star. How many do we think there are? So we fix this element. We know it's going to be in our k set.
N minus 1, choose k minus 1.
N minus 1, choose k minus 1. Yes, absolutely. We know it's in there, or we've already picked it, so we're going to fill out the rest of our set from a pool of n minus 1 elements, and we picked it, so we need to just add k minus 1 more elements. What about, and I guess we already know the answer, but let's think of the reasoning behind it. So what about sets of size k without star? Why, just looking at the answer we're supposed to get here, why is this n minus 1 choose k?
There's n minus 1 things that aren't star.
Exactly.
Beautiful. Beautiful. There's n minus 1 things that are not star, and we need k elements in our set, and we don't have access to star. So we pick k things from the rest of our elements. I like that I wrote star in words here. That's perfect. Okay, fine. So we have them that are containing it, have the ones that don't contain it. That's just all of our sets. This kind of goes back to that one proof that Corey did with A minus an element, sort of, kind of, it's sort of a paradigm, one or the other. Now that's one way to prove it. What else can we do? Let's see. We can double count binary strings of length n with exactly k ones. So I don't know if we made this explicit. I think we have before, but let's write this down. So n choose k, this is another way of denoting the number of binary strings of length n with exactly k ones. Oh, perfect, just like in the problem statement. And why is that exactly? Let's sort of think it through, is that what this is telling us is I have n many things, and I'm either going to choose it or I'm not. Choosing it amounts to a 1, not choosing it amounts to a 0. And if I have something of length n here, and I choose k ones, that is, that's my n choose k. Okay, now, how are we going to do that with, how are we going to count these binary strings? What can we do here? So in the first way we proved it, we said, okay, I can start north, I can start east. In this second one, we said, okay, I have the element, I don't have the element. What do we sort of think we're gonna do with this one? Do we have any hunches?
They start with 1 or 0.
They start with 1 or 0. Yes. Yes. And those two are mutually exclusive. That's what's really nice. Those two things cannot happen at the same time. And now let's hope that they actually get counted by the things that we want. Well, let's see. So we have, let's see, number of strings with, let's see, starting with 1. Okay, so we start with 1. We have exactly k ones, so what's going to happen here? Well, let's see, we've limited our pool to n minus 1 things. And we know we need exactly k ones. Our first digit, or first bit rather, is a 1, so we have k minus 1 other places to fill out our string. Or we start with a 0. And in this case, well, we fixed the first element, so we only have n minus 1 things to choose from. Awesome. And how many ones do we need to add here? Well, we started with a 0, so we still need to add k many ones. Awesome. Okay. That looks like Pascal's identity. Cool. Wonderful. My hands are already filthy. This is great. Don't rub your face. Just don't touch your face. All right. So, Pascal's identity. We'll sort of get to that in a second. We added this slide a little close to the talk because we think it's a kind of a fun little proof, fun little idea here, but it doesn't really fit in with what we're going to get into next. So it'd be nice to sort of give it a looky-loo first. So what do we have here? One, it's also, the name of it doesn't really make sense yet, but we'll see why it might. But we call this the middle binomial identity. I mean, maybe I call it that, at least. I think I named this slide, so that works. And what it's telling us is we take this sum of squares of binomial coefficients, and we somehow end up with this nice looking binomial coefficient on the right here. So let's look at that. Boop, bop, boop. Okay. That's n, choose, what do we choose? I. Okay. Let's see. I equals 0, n. And then 2, choose n. Before we even just go about this and sort of figure out just sort of this double counting idea, let's examine a small case here. Let's sort of see, can we even buy this? Let's do a small one. 4, choose 2. Okay. That is, if I picked n to be 2, we claim that this is the same as if we take sum from 0 up to 2 of the squares 2 choose I. Okay. Well, let's see. What do we want to do first? Let's do the right side. Okay, so 4 choose 2. Well, we can, I know what we can do here. 4 choose 2, that's the same as 3 choose 2 plus 3 choose 1. Let's just write that here. That's just that's just Pascal. And as we have seen 3 proofs of, it is true. So we can be safe to assume it. So 4 choose 2 is the same as 3 choose 2 plus 3 choose 1. And these are nicer numbers to compute. 3 choose 2 is how many ways we can choose a 2-element subset from a set of size 3. Well, that's the same as choosing 1 element to not be included in your set. So that is 3. And by the complement identity, another way of saying that, we get this guy is also 3, because 3 choose 2 is equal to 3 choose 1. That might be helpful. We'll see. So 4 choose 2, it equals 6. Nice. What about this guy? Okay. Well, let's write it out. So we have 2 choose 0 squared plus 2 choose 1 squared plus 2 choose 2 squared. Okay. Well, see, 2 choose 0, that's how many ways we can pick a 0-element subset of a set of size 2. Just a refresher, what do we get there? What is that? Yeah, it's 1. Perfect. There's one way to do it. That is to do nothing, which is a weird thing to think of, but it is the only thing. Any sort of brand of nothing is the same in our counting. Now, to choose one, sort of same guiding principle with these. It's just going to be 2. We square that, and then 2 choose 2. How many ways are there to choose a 2-element subset from a set of size 2? 1. It is 1 squared. Perfect. So we get 1 squared plus 2 squared plus 1 squared. That is 1 plus 4 plus 1. Oh my gosh, I didn't lie to you. It is 6. Okay. These do in fact equate to each other. That's wonderful to see. Now let's hope it actually works in general. I sure do. Let's find out. Okay. Let's just erase this biz. And okay. So what we're going to do here is we're going to actually do a double count here, but we're also going to use this identity that we brought up, I guess a little less than 12 hours ago. So let's just recall this is important, and I sort of used it a second ago. It's just this idea that the number of ways to choose k things from a set of size n is the same as choosing a set of size n minus k from that set. That is to say, if I choose k things from here, I didn't choose n minus k, vice versa. Okay, so why is that going to help us here? Well, I'm going to sort of tweak this side right here. I'm going to rewrite this. I'll just write it on the line below. This is the same as n choose I times the complement of n choose I, which is going to be n choose n minus I. Okay. And now this is the thing that I want to prove. Because if I can prove that this is true, then just use the complement identity, we get this guy. Just reverse that action I made right there. Okay, so I said we're gonna do a double count. How is that gonna work? Okay, so what we're going to do is, let's do binary strings. Why not? I like the flavor of it. So this right-hand side is going to count the number of binary strings of length 2n with exactly n ones. Okay. And now my hope is that this is going to count the same. How are we going to do that?
Cases based off how many ones are in the first n positions.
Thank you, Dan. Yes. Wonderful. So notice here, just sort of a nice sanity check is that the tops of these binomial coefficients, we have n and n, they add up to 2n. Oh, wonderful. Thanks, Corey.
I should have more though.
Appreciate it anyway. And at the bottom of these binomial coefficients, I, n minus I, those also add up to n. So there's this sort of relation going on with the two. And what is it? Well, we're going to say, okay, how many ones do I have in my first n elements of my string? So this right here says basically, I'm just going to look at the first n bits, and I'm going to say this is the number ways to get exactly I ones in first n bits. Cool, awesome. We have I ones in our first n bits, and so to get n ones, we just need to fill out the second half of the n's with n minus I ones. Now let's see, so number of ways to get exactly n minus I ones in second. Yeah, in the second n bits. Cool. So we can effectively, and the idea here is we can range from 0 all the way to n. This is sort of saying, okay, within my first n bits, how many ones do I decide upon? I can either have 0, I can either have 1, I can have 2, I can 3, all the way up to n. And once I've determined how many of those are in my first n bits, it's determined what's happening in the second. And there's not going to be any overlap there. And it's going to get me every single binary string. I feel like I don't have anything more to say there. But do we have any questions? Yay. Okay. So I should write bigger. Apologies for the folks at home. Hope I'm talking clear at least. Let's see. So now that was sort of a refresher in a way. So now let's get back to Pascal's identity and sort of what we can do with it. Let me make this a big picture. Ooh, there we go. And I'll cut that. Awesome. So Pascal's identity, to come back to that, it allows us to recursively build all of our binomial coefficients. If I know 0, choose 0, 1, choose 0, 1, choose 1, I can get every single other binomial coefficient that I could possibly want. And now this Pascal's, and then we get Pascal's triangle, which is this object right here. You can see there are some patterns that are drawn on here that we're going to investigate in a second. Before we do that, let's sort of build our triangle. Let's get first maybe 4 or 5 rows. Okay, so 0, choose 0. That is 1. Yes. Okay, we have one way to, choose 0 things from a set of size 0, of course. Now what about 1, choose 0? That is 1 as well. 1, choose 1. 1. Okay, and how do we get there? Well, we just added 1 with, we can think of this as like a 0 off to the side, and then another 0 off to the side. We just added those to the 1 to get these values right here. Now to get our next row, we can just sort of take these 1s along. And to get this middle part, we're just going to add 1 and 1. Just going to take these away, that's sort of distracting. Okay, we get a 2. All right, wonderful. And we can keep doing this. Bring these 1s over, start adding things up. We get a 3, neat. Keep going. 1 and 3, you get 4. 3 and 3, you get 6. 3 and 1, you get 4. And 1 and nothing, you get 1. It can be kind of meditative in a way to just keep on writing this triangle down. You know, you start seeing some patterns. You start kind of just losing yourself in the minutia. But what do we actually get here? Well, let's see. So we have this picture here that sort of hints at some structure with our triangle. What is that? So we have these rows. Let's look at those rows. I'll do one more row here. There we go. Okay. So what happens if we sum our rows? Let's add them all up and see what we get. Okay. 1 plus nothing. That's 1. 1 plus 1. That's a 2. 1 plus 2. 3 plus 1. That's 4. Oh, I think I'm seeing a pattern. 1 plus 3 plus 3 plus 1. That's 8. This is 16. This next one is 32. Just sort of pick up on these things, you know? I bet you this next one's 64. Why? We've actually seen this before. We've seen this a few times. This is actually something we sort of proved a few times here. What this is sort of saying is that if you sum up the binomial coefficients of a fixed n, then you get the nth power of 2. What is that saying? Well, let's write it out. And I feel like we've avoided the sum notation until recently, so I'm just gonna do it. Why not? Okay, I from 0 to n of n, choose I, is equal to 2 to the n. That is the claim here. This n choose I from 0 to n, that's everything in the same row. And now we want this to be equal to 2 to the n. Luckily, that is the case. Because what is 2 to the n? That is the number of subsets of a set of size n. We've seen this a few times. And what are we doing on this left side? We are just figuring out the counts of subsets of every size. All of them size 0, 1, 2, 3, 4, all the way up to n. Okay, wonderful. And that's nice. We get to see that in Pascal's triangle. Wonderful. Now what else do we get? We get some weird looking things that maybe at first glance and maybe second glance, and maybe, you know, you do a homework problem about it and you think a little too long, which is always good. Always think for way too long, you'll find something. Might be a panic switch, but you'll find something. So what is this? What are we seeing here? We see these things, it's called this hockey stick identity. What is it even sort of saying here? We're trying to relate these 6 elements, oh my gosh, a pizza. Let me actually leave these. Let's leave this, leave this, leave this. Okay, so what is the hockey stick identity? Let's see. So we're always starting on this part of our triangle on the right, top right corner of it. Oh, oopsie. Oh gosh, no, you're good. I'm fidgeting with the stream. You're chilling. Okay, and so what do we have? We have starting from the top right of something, going down a diagonal. and then
Whatever you want.
finishing out a hockey stick. Okay. I'm also going to take a slice. Sorry, y'all. Just gonna be part of the talk. What is that, Daniel?
What about all the viewers?
I know the viewers can watch me eat, but I'm gonna do math while I eat. Trust me, I can do it, I swear. Okay, so what are we actually doing with this hockey stick here? So, like I was saying, we can draw this sort of hockey stick shape. We start at the top right corner here, and we go down it until we decide to actually make the head of this hockey stick. Now, how are these values relating? How is 1, 2, 3, 4, and 10 related here? Do we see it?
1 plus 2 plus 3 plus 4 equals 10.
Everyone see that? Yes. What about, let's just do another one, just to see if maybe we just sort of thought up a pattern, we got lucky. That does happen a lot with math. You draw enough pictures and you land on the one that was just right. But it was just right because you chose it that way. Well, let's try this one. Okay. I'm doing the small hockey sticks because I just didn't want to draw the triangle too big. But let's look at this guy. Does this follow the same pattern? We have 1 plus 4 plus 10, and that is 1, 5, 15. Okay, we have a pattern here. We take the stick of our hockey stick, add it all up, and we end up with the hockey stick tip. Let's prove it. One of the things that's sort of fun with binomial coefficient identities is not only do you sort of get to find these patterns, but then you actually have to sort of give it a closed form. Because yeah, I can show you, like, yeah, 1, 2, 3, 4, I add those up, I get 10. 1 plus 4 plus 10, that equals 15. But if I want to prove it, I want to prove a general statement here. So let's relate back to, I'm going to put up this picture of the big binomial for a second. Where am I getting this 1, 2, 3, and 4 from? Well, that's 1 choose 1, 2 choose 1, 3 choose 1, 4 choose 1, and 5 choose 2. I'm going to write, I keep accidentally, oh, no, there we go. There we are. Okay, let me write that down. So that's 1 choose 1 plus 2 choose 1 plus 3 choose 1 plus 4 choose 1 equals 5 choose 2. Okay, that's one instance of this hockey stick. Let's do this other one right here. We have 1, 4, 10, and 15. That is, what is that? Is that 3 choose 3? Yeah. That's 3 choose 3 plus 4 choose 3 plus 5 choose 3 equals 6 choose 4. Make sure that I'm not losing my marbles. Let's look at that again. Yes. Okay. Do we see a pattern going on here? Let's see. So we fix the k in our binomial coefficients on the left, and they add up to one that is greater. Okay, that's one part of it. We always start with a binomial coefficient that's n choose n, and then we start just adding from the top there. Let's sort of like write that down like so. So we start, we're gonna write this as a sum, and we're gonna start at 0 because that's sort of how we like to do things. Let's try it out though. So we're gonna fix whatever this bottom part is. Let's say it is k. Fix that k, and now we wanna go and add up, or we wanna change the top of our binomial coefficient. And what is that going to actually look like? Well, we start at k, choose k, and then we start adding up by 1. So starting at I equals 0, we can then add 1, add 2, add 3, add up to some n, whatever we decide. And now what should we expect on the right side if I chose n to be my end point here?
N plus 1.
Not quite.
N plus 2.
Keep going. No. Anybody else? Anybody else see?
And choose k plus 1.
Let's see. It was n choose k plus 1. It's close. So I like the k plus 1. That's spot on. We had all of these with this fixed k, and then we got a new one. Cool. But let's look at this string right here. We go all the way up from 3 choose 3, 4 choose 3 to 5 choose 3, and then from this top value right here, we add 1. What's the largest value that we get right here in our sum?
K plus n.
K plus n. So we'll actually get right here, and I'll write it like that too. K plus n plus 1. And this is your hockey stick identity. How do we prove this? I assume there's multiple ways, but what I'm gonna do is a induction proof. I think it'll work out kind of clean. We could ask ourselves, like, what would a double count of this be? And I mean, hey, there you go. There's some homework for you. Can't say you didn't learn something.
So you can do binary strings of length k plus n plus 1 with k plus 1.
Van, no. We can do that. Yes, binary strings can often be the way to go. In this case, I think you should be fine with binary strings. But I'm not going to do that. I won't allow it. I'm going to do proof by induction because why not? Let's have a little.
We haven't seen enough of those.
No, not at all.
With binomials.
Exactly, not with binomials. So let's sort of see what we can do here. And I actually didn't prep this, but I think it'll work out just fine. What are we inducting on? Is my question to you.
What is the limit of the sum?
Oh, sorry, it's
No,
this.
I mean, I'm no way.
It's n.
I would guess on n. So that we get another term.
Yeah, I think we're gonna induct on n. Let's do that. We're gonna fix k. We're gonna induct on n. Let's see what happens here? So base case, let's see. We have I equals 0 up to, what would our base case be here? What value of n is the smallest that this makes sense for? 0. Why?
You can do 0, choose 0.
That's true. Also notice in our sum here, we evaluate from I equals 0 up to n. So we're allowing that as a minimum value there. Yeah, and that could just be the one thing. We could have, if you're feeling fancy, we could have done that. It would have just had the one term where n equals 0. But yeah, absolutely. So what happens here? N equals 0. I think I just said it, but the left side right here, it is the sum of just k plus 0, choose k. Let's write that here. K plus 0, choose k. That's this left side. That's k choose k, which is just 1. Oh gosh. Is it? Oh, never mind. Okay. And then what about the right-hand side? We have k plus 0 plus 1, choose k plus 1. Oh, thank heavens. My k's are k's. Okay. That also equals 1. So, we're good. Awesome. Now let's let n, let's let I, yeah, let's let I be greater than or equal to 0. Why did I do that? Let's just do this. Yeah, n be at least 0. And let's assume that this holds for n. Let's just assume this holds. Yeah. Ba, ba, ba. Okay. All right, so we're gonna assume this, but what we really want is this sum with one extra element. So let's see what that looks like. We have, just gonna do it right here. I'm gonna add, no, let's not do it there. Okay, we are going to add to k plus I choose k, the n plus 1th potential term here, whatever that would be. That would just be k plus n plus 1 choose k. K plus n plus 1 choose k. And that is going to be equal to k plus n plus 1 choose k plus 1. I added this over here, so I'm going to add it to this side as well. This left-hand side is just the sum going up from 0 to n plus 1, which is what we want. And now what do we have here on the right? Anyone see what's going on there? Because what do I want this right-hand side to be?
K plus n plus 2, choose k plus 1.
Yeah, we want k plus n plus 2, choose k plus 1. Is that what we have right here? Whoa. Yes. We use Pascal's identity here. These two, we can think of these as just an n minus 1. We tack on 1 to both of those. And then we have a k and a k minus 1. We end up with a k, which is, in this case, k plus 1. Maybe I could have, no, that would have had to make the, no. It works out. This is true. We got that by Pascal's. And so we have base case. We got our inductive step. It turns out we are done. We got it. There we go. That's the last induction, I think. Maybe not. We'll see.
Don't be so sure.
Oh, last induction in my section. Maybe. Let's see. What do we got now? Okay, this next one I'm not going to prove. I did not prep it, and I've looked at Stack Exchange and thought, oh, this is sort of just outside of what I think is beneficial, and also was kind of tedious to try and figure out. So we're just gonna do this sort of setup that we did here, and just sort of try and figure out a closed form that we might want to try and prove. Not one that will actually prove, but sort of something that maybe if we were, open to, we could prove this. So what do we have here? We have these hexagons, these blue hexagons on our triangle. And I am going to speed around and build a triangle again, because we are going to do some math. Oh yeah. We're gonna see what we do here. You don't know what we're gonna do, but we're gonna find out. There we go. Okay, awesome. That seems like enough. So we have these hexagons. Let's just pick some hexagon here. We have 1, 2, 3, 6, 4, and 1. Okay. It's definitely not obvious what to do with these, but let's see. I mean, I know what we're supposed to do. I'll admit. But let's see. So the last one with the hockey stick, we added up terms and we got something nice. I don't know. Let's try and add things up here and see what happens. What would you even try and add up? What would we even want to see here? Does that we see anything going on with 1, 1, 2, 3, 4, and 6? It's.
Could you multiply 3 of them?
Ooh, okay. What would you multiply?
Split it into 2 pairs of 3 that are separated.
Okay.
Like 1, 2, and 6. Or I don't know about that, but
Let's draw it. Let's see what your suggestions. We got. Oh gosh, I don't like that. Green. Is this green okay? Oh gosh, please don't ruin the board. Okay, so you're saying this 1, this 2, and this 6. Okay, and multiply those. Let's see what we get. Ooh. 1, 2, 6. Okay, I don't know, Van.
try another hexagon.
I'm gonna try another hexagon. Which hexagon should we try?
Something centered around a 10.
Yeah, 4, 6.
Let's do this one. And we'll do the same sorts of triplets. Okay, we got 6, 5, and 20. And we also have 10, 4, and 15. Why did I say it like that? I'm not even writing it that way. 4, 10, and 15. Okay. Let's see, what do these equal? We got 6 times 5 times 20, so that's 600. Yeah, okay. And then, golly gee, wow.
I don't think it's a coincidence.
I don't think it's a coincidence. Okay, wonderful. So, now let's see. What is this non-coincidence? Let's try and formalize it. So, how do we want to do that? Well, we have rows, so let's sort of name our rows. We got, this is the first, this is the second, the third, the fourth, fifth, sixth, seventh. We can also just say, you know, let's look at this hexagon in particular. Let's think of this maybe as our nth row. Okay, this would be our nth row. Then this would be our n minus 1th row. Yeah, sure. I'll go with it. Because I'm also going to say n plus 1th. Just
I think
cause.
it's n minus word.
What if you,
Minus 1.
N minus, yeah, n minus, and yeah, I think you're right, Dan. N minus word.
work around and choose K? So like the center you name? Mm-hmm. And then you call those all relative to n choose K there. Maybe that's what you're doing. Mm-hmm. Is that what you're doing?
I think so, yeah.
Oh, okay.
Yeah.
I misunderstood.
Oh, so yeah, I guess I was sort of building it up like, because yes, we are going to build it around the center, and if this is our nth row, then the center will be at n. But yeah, I like your suggestion, Corey. Let's think, and also I don't think I have made it explicitly clear. Let's look at the triangle again. Notice how, oh wait, it doesn't get bigger. Oh, like there's people at home, so I do want this to be bigger. I'm just a little tired, I'm sorry. Okay, so how is n, like n is fixed along these horizontal rows, and k is fixed along these diagonals. That is important here. We sort of needed it in our last problem, but I didn't make that clear. These diagonals are what, this is how we fix our k values. So if this is our nth row, let's make this our kth diagonal. And let me make sure to make this big again. There we are. Okay, that'll be our kth diagonal, which makes this our k minus word diagonal. And that would make this, yeah, why not? I'll just finish with the same color. Our k plus k plus first diagonal. Okay, so with those pieces, I think we can sort of formalize this hexagon identity. Let's see, so we got we have two products that we're trying to relate. Let's just sort of write, let me actually draw it at the bottom here, give us some room. This is, okay. Let's build these hexagons. Okay, let's do this triplet first. So this one, and this one. This 1, this 2, and this 6. That is, let's see. So this 1, it's in our k minus 1 diagonal, and it's in our nth row. So this is going to be n choose k minus 1. And we're going to multiply that with, this is n minus 1, choose k. And there wasn't really a particular order that I decided to choose these choose functions. But this one is going to be n plus 1 choose k plus 1. Or n plus 1, did I say? Yeah, whatever. N plus 1 choose k plus 1. Okay, so that's our first diagonal. Okay, we have like 3n things, and we're choosing 3k in some particular way. Okay. Now, what's the other one? We have n minus 1, choose k minus 1. Okay, let's see, what's this one gonna be? Just sort of following the same sort of scheme. Yes, precisely. N, choose k plus 1, and then what are we missing? We're missing this fella. What's that gonna be? Perfect. Awesome. So now we have this product right here, this product right here, and there we go. Perfect. That's all I got to write. So we're not going to prove this today. I was looking into this problem, and I've seen people discussing it as sort of, we take an arbitrary number right here, instead of a 1, I think we can take like an I or an R here and do that in each of these spots. And it'll actually be an easier problem to solve. And then this is sort of a specific case of it. I have not prepped that, and I'm not going to try and work through it because I think it might be a little more complicated. But this is true. There are ways to show that it's true. And if you do just look up hexagon identity, you might be able to find some people talking about it on the internet very aggressively. Yes, Anna?
So, I mean, I'm not suggesting you do this at 2:45 in the morning. But like in theory, we've always
nice.
proved these things by having like a clever double counter or something. But in theory, if you didn't have any ideas, you could just like take the left-hand side and expand it into factorials and manipulate them.
You're absolutely right, Anna. That actually, and you know what? Just for practice, it might just be sort of a gross to do, but you're right. If all else fails, if we don't know how to combinatorially prove such a statement, we can fall back on our numerical numerical identity of the binomial coefficient. So let's actually sort of start that. Let's see. Let's sort of expand this thing. What do we get? It's gonna look wonderful. So n choose k minus 1. Well, that's n factorial divided by k minus 1 factorial times n minus k plus 1 factorial. Whew, already sweating. Times n minus 1 factorial divided by, we got k factorial, and n minus 1 minus k factorial. And then we have n plus 1 factorial to divide by k plus 1 factorial times n minus k factorial. And now we're hoping this is equal to the right-hand side. And this will actually probably be kind of nice, I think. Let's see. We have n minus 1 factorial divided by k minus 1 factorial times n minus k factorial times n factorial times, or divided by this wonderful thing, k plus 1 factorial times n minus k minus 1 factorial, and we're almost done, times n plus 1 factorial divided by k factorial times n plus 1 minus k factorial. And this is actually, I think it's not too bad to see that this is true, because multiplication is commutative. So what do we got here? So on the top, like if we just sort of expand both of these into just big old fractions, because that's totally fair and reasonable. You multiply a fraction with another fraction. You get a fraction with these parts as your numerator and this product as your denominator. Let's just sort of see if we get the same things on both sides. The numerators, definitely the same. We got an n factorial over here, n factorial over there. Same with these two. Awesome. Now, the denominators are going to be a little jumbled, but I think we have everything we want. So let's sort of, I'm going to cross them out just to sort of check that we got them. So we got k minus 1 factorial right over here. I just crossed it prematurely, but it was right here. So cool, it's right there, it's right here. We got it on both sides. Let's do another one. N minus k plus 1 factorial.
Very end.
I see it, it's at the very end. Huh. But I wrote it weird. Perfect, but it's the same thing. N plus 1 minus k is the same as n minus k plus 1. Perfect. K factorial, we got them. N minus 1 minus k, we got them. K plus 1, we got them. And n minus k, we got them. These things are equal. They have to be. And this is not a really nice proof, but it's true. Look at that. I'll put this right here just to show that I actually did the thing. And this right here to say that we've concluded it. This is perfect. Yeah, thanks, Anna. That was a wonderful suggestion. And it does sort of, yeah, it indicates that, you know, push comes to shove, at least we know like a numerical value of our binomial coefficients. And that can be a way to check. Sometimes it can be a way to check.
Off the top of your head, does that same like kind of brute force method work with the other proofs that we've just discussed so far?
It will work with, I think the first two.
Okay.
Yeah, the first two, I believe you can get away with it. Yeah, and sort of going off of that, how I was discussing this like n divided by k times n minus 1 choose k minus 1 equaling n choose k. It does sort of flow out, like using, if we think about this with the factorial identity, because what do we have right here? This is n minus 1 factorial divided by k minus 1 factorial times n minus k factorial multiplied with this. Thank you, I should have added this earlier. I really do appreciate that. And so what happens here though? So we have n times n minus 1 factorial, which is n factorial, and k times k minus 1 factorial gets us k factorial. We have this. That's perfect. That's exactly what we'd hope it would be. So yeah, some of these you can like brute force check it. It's not elegant. It's often, yeah, I don't know. In these cases, it'll work. But
I encourage you to try to prove that n factorial over k factorial n minus k factorial is an integer just by looking at the factorials though. Some of them are, some identities that are pretty easy to do to count are like almost impossible to do.
That is
Just
it. Yeah.
Just the numbers.
That's a good way of looking at it, Van. Yeah, that's the trouble with this is that you can do it to sort of check if like the algebra is working. Just from first glance, though, as Van's kind of pointing out, what of this is indicating to you that this is actually going to be some integer? Because we know that our binomial coefficients always going to be some positive integer. They're just these entries in our triangle. But this is a fraction involving factorials, which are these nasty large numbers. Yeah, good point.
Of course, it does, like, I mean, I don't, this doesn't, I have no idea why the hexagon identity is true. Or is reasonable from the algebraically.
Algebraically, it works,
Well,
which
I think
it's
the
not a good
argument
proof.
is, I mean, it's elucidatory based off of, I mean, you just replace every one with an R, and then it shows the general form.
Yes.
Right, but like combinatorial.
But combinatorially, that's the thing.
For what's
If you want to do combinatorics, then this is a good way to just make sure you're not crazy, but this does not make a good proof. A good proof it does not make is the fancy way of saying that. Okay, what are we doing? I think this is the last one of this flavor. I think I'm gonna skip this one though, unfortunately, because I wanna get into the binomial theorem, and I didn't realize I was sort of dragging my feet through the mud here. This is a very cute problem though. I'll sort of sketch the idea of it. It turns out if we add these, say, shallow diagonals of Pascal's triangle, we end up with the Fibonacci numbers. And it's actually kind of cute that the way we can actually prove that this holds is just by using Pascal's identity on two shallow rows and getting a third shallow row. I'm gonna leave that to the interested viewer to investigate. But I want to get to this. I think with a little over an hour left, I think it would be important to discuss this. This is the binomial theorem. This is a wonderful, precious tool, and it's got a binomial in it, so the name checks out. So what is this telling us? This is saying, and this also is sort of where the name binomial, I guess, comes from, is that a product of the form x plus y, it has two terms, binomial, is something of this form, x plus y raised to a power. And the binomial theorem effectively tells us what the coefficients of this polynomial are going to look like. It's going to be n choose k for the x to the k, y to the n minus k term. And you know, we're not unfamiliar with some of the consequences of this theorem. You know, we've written out, we've done, say, x plus y squared before. You know, it's x squared plus 2xy plus y squared. But perhaps it wasn't, and I mean, most likely, it wasn't obvious that these were binomial coefficients that we were using as the coefficients of this binomial. Go figure. But in this case, with x plus y squared, what are our coefficients? Well, it's 2 choose 0, 2 choose 1, and then 2 choose 2. just so works out here. But why does it work out? That is what we are going to prove right now. Okay, so we're going to do a double count, of course. So what we're going to sort of figure out is, well, how many ways are there to choose k x's and n minus k y's when expanding this thing out? See, Daniel? Well, let's think about it like this. So x plus y to the n, it's a product with n versions of x plus y. Now, if I'm going to figure out my x to the k term with, or x to the k, y to the n minus k, then what I'm effectively saying is I'm going to have to pick k x's from this product here. Like when I multiply these out, I'm gonna get a bunch of things going on, but for just looking at this term right here, if I pick, say, I'm gonna pick x from here, y from here, x from here, in such a way that I've picked k x's, then I've picked n minus k y's as well. And and the fact here is, how many ways was I able to choose an x in this process? Well, I had two choices at each step, and the steps, it actually didn't matter how I chose it. I had, oh my gosh, hello. Is that my watch? No, it's not. Okay. No worries. It kind of helps in a way. But we have n choose k ways to choose k x's. I could have chosen it from here, any k, I guess I can say this is n terms. And then I could have chosen from any of these k. But once I've chosen a particular k arrangement, that's in my count. And I'm just gonna pick every type of way that I can choose k x's from this product. And that will end up being n choose k. And like I said, once I've chosen k x's, I get my y's for free. They're part of the expansion as well. And so we just sum over all possible values of k, and voila, we get the binomial theorem. Now what can we do with this baby? Does it got wheels? Let's see. Let's do some expanding. Okay. Before I go on, do we have any questions actually?
Is there a trinomial theorem?
I took it away from the slides. But there is a trinomial theorem, yes.
Or a quadrinomial theorem?
Probably. I think so. I think the idea is you have an alphabet. So in this case, we have x and y, and you determine how many ways we can choose x's and y's so that our powers add up to n. And if we start adding extra guys in here, say we added z, we could get a trinomial theorem where if I choose k x's, then it's not necessarily determined that I've got n minus k y's. And when I say this, I'm adding a z to each of these. I then, after I pick my k x's, from the remaining choices, I'm going to figure out what's happening with my y's and z's. So a trinomial theorem, you can express it like a sort of weird binomial thing if you want. But for now, I'm going to do some binomial action. Let's do it. Let's expand these. What's x plus y cubed? X plus y to the fourth? I don't know. Let's find out. Okay, well, what does this tell us? Okay, so we're going to go from 0 to 3. Easy. That's the first one. Okay, we have these matching. We got a 3, choose 0. What's that going to be the coefficient of? Well, we chose 0 x's, and we chose 3 y's. Yeah, usually I'd start with the x's, but I wanted to follow this. It works out in the end. It's symmetric in a certain way. So, but whatever. Any case, what do we do next? I feel like I'm doing something wrong here. Nope, I'm not. Just felt weird. Okay. 3, 2. Something does feel off. What am I doing here? Something's wrong. Nope. Everything's okay. We're okay. I'm tired. It's coming out right now. Okay. We have 3, choose 1, and then what do we got? We have 2 y's and an x. Then we got 3, choose 2. We have 2 x's and a y. And we've got 3, choose 3 as our coefficient of x cubed. What's that? So what does this actually end up being? Just y cubed plus 3xy squared plus 3x squared y plus x cubed. And if we run through this again, and I'm not going to go through all of the rigmarole, but if we expand x plus y to the 4, I'm going to start with x's this time. Bear with me. We get x to the 4 plus 4. Thank you. 4x cubed y plus 6 x squared y squared plus 4x y cubed plus y cubed. 4. Perfect. And let's just sort of, where am I getting these numbers from? This is, again, just to sort of reiterate the whole time, and I've been in the small screen, but I think we can see it still. It's the binomial, it's Pascal's triangle. It's just a row of Pascal's triangle, of course. Wonderful. Oh my gosh. And now we have this problem. I am going to, let me see, what do we have after this? Maybe, you know what? I'll do like 2 of these ones. These aren't so bad. So what do we got here? So yes, we can use the binomial theorem to expand some binomials, but yeah, sometimes we'd rather not expand the whole thing, and maybe we just want a single term. I'm just going to move the binomial theorem to the top left corner. Bear with me. X plus y to the n equal to this sum. I equal 0. Okay, there's our binomial theorem. Now let's let's expand one of these. Which of these looks enticing to the crowd?
D.
Perfect. Let's do it. Okay, so find the coefficient of x to the 5 in the expansion of 2x. All right. See, 2x minus 1/2 y to the 10. And we want to figure out our x to the 5 coefficient. So what's that going to be? Well, let's... Wait a second. No, it's okay. So, oh, is this a trick question? Wait. Oh.
I think we will only change the sign.
Why am I? Okay. Oh, okay. Well, I'm losing my steam. So what is the coefficient of x to the 5, everybody? Oh, well, that's the issue. For some reason, I'm forgetting. Okay, we got this, I swear. All right. 2x minus 1/2 y raised to the 10. We want the coefficient of x to the 5. Okay. So let's sort of so let's wait before we get to that. Let's just look at the setup of our formula. We have x plus y raised to the n, and then all this stuff on the right. In this case, our x is 2x, and our y is minus 1/2 y. So on the right-hand side here, we'll just sort of get in the basic setup. Let's write this out. This will be, everything will sort of stay the same until we get to our x and y here. What we'll have is 2x to the k, and then we will have minus 1/2 y to the n minus k. Okay, so now what do we get here? So if we're looking at x to the 5th term, well, let's look at it. We got, oh, there we are. Last thing that I forgot. We're going to 10 here. Wonderful. And then this is 10 minus k. Okay. So when x is raised to the 5th power, that's when k is 5. So we got 10 choose 5, 2x to the 5th, and then minus 1/2 y also raised to the 5th. And we can expand this a little bit more. We have minus 1/2 raised to the 5th and 2 to the 5th. These will actually just sort of collapse into each other and leave us with a minus 1. And so we get a minus 10 choose 5. I'm going to move this y 5th to the front, and then x to the 5th in the back. And so our coefficient is minus 10 choose 5 times y to the 5th. Cool. All right. Let's see. Let's do one more of these. Let's do E. Find the coefficient of x to the 8 in the expansion of x squared plus y to the 7. Let's do it. Let's see. We got x squared plus y raised to the 7. So what do we do here? Our n, in this case, is 7. And now x is x squared, and y, we have this 7 here. So what is different about this problem? What's the curveball thrown here? What value of n do we need to use? Or k, rather. Sorry.
4 in this situation.
Yes, my bad. Yes, you were right, though. Your answer was correct. We did need to use 7. And yes, exactly. We need to use k equal to 4 because of this square right here. Yeah. So the coefficient, we get 7, choose 4, x to the square, or x squared to the 4th will get us 8. And then y is raised to the 3rd power. Perfect. Nice. Okay. So that's one sort of power of this binomial theorem. Let's look at some others. Let's look at these. Let's make these a little big. Let's take me out of here for 1 second. Okay. So I don't know why the formatting is the way it is.
So you can have the box on.
Oh my gosh. Oh, wait. Not like that. There we go. Oh my gosh. That's so sweet. Okay. Yeah, all right. That makes a lot more sense. So, yeah, we have these identities here. So we've already seen this first one a lot. This is just saying the sum of the binomial coefficients is equal to 2 to the n. Okay, but we were going to prove this using the binomial theorem. What does that entail? Let's see. So I want to show something about 2 to the n. Let's see, 2 to the n. I want to rewrite this as a binomial. By that I mean I want to write this as like an x plus y to the n. So it really actually, let's see, does it matter in this case? I think it kind of does. Yeah, I mean you could do it in some other way, but let's think about it like this. I want to show 2 to the n is equal to just this sum right here. N choose k times nothing here. But the binomial theorem tells me that this is true. Similar setup, but now I have this x to the k and y to the n minus k. So it turns out, if I just choose if I make the right choice of x and y, then I get this first formula right here. Do we see what that is? Mm-hmm. Absolutely. If we set x and y equal to 1, what happens here? We get 1 plus 1 to the n. It's just 2 to the n. And then on this right side over here, we have same thing. We got this sum going on here, and choose k. And then we got 1 to the k, that's just 1. And 1 to the n minus k, that's just 1. Cool. Right on. Kind of neat. Let's see what this next one is. So, this,
Could I ask a
oh,
question?
yes.
So why can't we use like negative values for x and y, I guess? Wouldn't that open the gate to more possible values of them to equal to?
We could allow x and y to be negative.
And we'd still get the same thing?
The binomial theorem, it would still hold.
Interesting. Okay.
Yeah.
Okay.
Yeah, x and y can be any real value, actually. The only thing, and we can also, and this is totally past this sort of discussion, but we can even expand this to go past just our regular old like 1, 2, 3, 4, 5, 6. We can use other numbers for n here. We don't need to go there. We don't need to go there right now. I'm a little fuzzy on it. It's been a while. about when that actually holds. But in any case, yes, x and y, they can totally be negative. If we go back to the previous slide too, you'll see we have at least, the one that we did was the 2x minus half y raised to the 10. That there, if you think about that minus, or if you think y as like a positive number, then that minus makes it negative in some instance. So let's see. But yes, okay. Any other questions? Cool. Let's do another one. So again, we're just trying to use this theorem to prove some other statements. Now we have this one where take this sum n choose k, 2 to the k, and we claim that's 3 to the n. And this is effectively like the same idea that we just used. And what it is we set x equal to 2 and y equal to 1. And then we can sort of see this is the same if we had an n minus k, 1 raised to the n minus k here, it just sort of goes away. And 3 to the n is the same as 2 plus 1 to the n. Oh, excuse me. So we get this really weird sort of formula. It works out. You can write a power of 3 as this sum involving binomial coefficients. And now one of my favorite identities, which it's just again a use of binomial theorem, is that if we sum up, oh gosh, k, there we go, it's a k. If we take binomial coefficients and make every other one negative, so sum up the binomial coefficients, make every other negative, this will get you 0. Yeah, and without even using the binomial theorem, for some of the rows of the triangle, this seems kind of obvious. You know, one of the row, like just sort of looking at these rows, they're symmetric in a way, which, and this mindset of it really only kind of works for some of the rows of if we're thinking about it this way. But just looking at, like, say these rows in particular, we have like something to match each element. So if we just alternate the sign of each of them, this will subtract this will subtract this, and this will subtract this, we'll end up at 0. Where it's not immediately obvious are rows like this. It does work, 4 plus 4, you get 8, 1 plus 6 plus 1, take the negative of that, you get negative 8, perfect, we're safe. But we don't even need to sort of work with why this is true. We can prove this without using the binomial theorem. I'm not going to right now though, because this is about the binomial theorem. So what do we do here? Well, this is great. We sort of see it on the left side here. We have minus 1 raised to the k. That's our x. And y is missing. So that, in a sense, means that y should be equal to 1. So is that true? What does that mean? That's saying this right here is equal to 1, that's our x, or sorry, rather, let's do this. Minus 1, that's our x, and y is 1. And then raise that to the nth power. This whole thing is going to be equal to this by the binomial theorem, but -1 plus 1 is just 0. So we get exactly what we want here. Oh, excuse me. Okay, let's see, where are we at? Nice. Okay, so what else can we do with the binomial theorem? We can, we have this inequality. It's, I believe it's called the Bernoulli inequality. Bernoulli, mathematician, he used this inequality. I can't see why, because, I mean, I don't know. I guess it pops up a few times. I've looked at the Wikipedia page, and it's like, there's like 5 different variations on it. But why I am just sort of, I don't know, laughing at this idea here. So let's sort of look at this problem. So we want to use binomial theorem to show that 1.01 raised to the 1,000 is greater than 11. Okay. If you wouldn't mind, Van, could you plug 1.01 to the 1,000 in your calculator? Just any old calculator. You can even plug it into my laptop. Just,
I've done so.
what's that?
I've done so.
You've done so. All right. All right. We're gonna leave this open about what this is approximately equal to. Before we figure that out though, what we wanna show is that it's greater than 11. Okay. Well, let's use the binomial theorem here. We can sort of break this apart into being 1 plus 0.01 to the 1,000. Okay. Now, what does that tell us with the binomial theorem? Well, this is equal to, let's just look at our sum here. Going from 0 all the way to 1,000. 1,000, choose k, and we got 1, yeah, it's 1 to the k, and then 0.01 to the n minus k. Okay. Now, what can we do here? Well, there are 1,001 terms here. So I would rather not worry about all of them. So I'm just gonna look at the very first and the very last term. Let's see what those are. So the very first term, that's gonna be 1,000, choose 0, which is gonna be that times 1. And I might have wanted this to be, I feel like I'm doing this wrong. Let me see. I'm just gonna roll with it. Okay, well, first of all, this should be a K. Doesn't matter though. Oh gosh. I've been lying to you all. Okay, cool. All right, so this should be this, and I'm feeling unsure of myself. You know what? Losing it. I'm gonna skip this problem, but before I do, I'm gonna skip it because I only have about 30 minutes and I kind of want to work on a more fun problem. But before I do, and apologies, I'm so sorry, viewer at home. I know, you want to know, why is this true? But lucky for you. Ben, what is 1.01 to the 1,000?
20,959.
20,959. Don't worry, that's greater than 11. Thankfully, we did it. And funny enough, yeah, Corey, originally the problem was stated as this being greater than 1,001, which doesn't follow from the second half here, but is definitely true, which is good. But
Does this end up working? So I'm just looking at this.
Yeah.
If you look at the last two terms,
is it the last two terms, Van? Because that's, yeah, okay. Just a little dull. Yeah, so let's look at this guy. Yeah, thank you. Because it was a poor choice of my k and my n minus k here. Yeah. So that is this guy raised to the 1,000, and then this raised to the 0, plus, let's not even worry about this guy, and then 1,000, choose 999. Cool. 1 raised to the 999 times 0.01 to the 1. Thank you so much. I'm losing my voice. Yeah, the home stretch. We got this. Okay, so I chose a poor. I did it poorly. I just chose the wrong things. It's okay. I've been in the small screen this whole time. It's not okay. There we go. So that's actually good because nobody could see the wrong work. So let's see. Let's actually go back to what I was even saying. So we got our x is 1. We got our y is 0.01. We got n is 1,000. That's equal to this by the binomial theorem. And that's a lot of terms. So we're just going to look at the last two terms. That is 1,000 choose 1,000 times 1 to the 1,000 times 0.01 to the 0 plus 1,000 choose 999 times 1 to the 999 times 0.01 to the 1. What are those? Let's see, 1,000 choose 1,000 times 1 to the 1,000 times 0.01 to the 0. What's that one? 1. Perfect. And then let's see, what's this next one? 1,000 choose 999. That is 1,000. Okay. Times 1 to the 999. That's 1. And then times 0.01. Ah, perfect. And 1,000 times 0.01, well, that's just 10. Perfect. So what we have is 1.01 to the 1,000 is greater than 11. Wonderful. And what we can see in general is if we just take an arbitrary x and n here to sort of do a little bit of substitutions. So this 0.01 is taking the place of an x, this 1,000 taking place of n. Just following this proof all the way through, we end up at this same part right here where it's 1 plus, instead of 1,000, we have just our general n, still only 1 to the n minus 1, which is 1, times x. And so we end up with 1 plus n times x, always being less than 1 plus x to the n. Thank you, Bernoulli. You solved it. Okay. Now, let's do this one. Okay. we've all taken calculus, right? You know, like, hi. So in calculus, we have these things called a Maclaurin series. And a Maclaurin series is a way to approximate a function near zero, near x equals 0. And it's a way to approximate a function with polynomials. And if you haven't seen calculus, I apologize for this next problem, but I think it's kind of fun. So we're gonna vibe with it. Let's see what happens. So we are gonna recall that the Maclaurin series is given by this formula. What's this formula say? Let's actually pull this back up. Okay, it says f of x is equal to the infinite sum over the derivatives of your function at 0 times x raised to the k over k factorial. You take the kth derivative for all k's possible, and you do this here formula. So we're going to assume that this is true. We're just going to assume this holds, and we're going to somehow end up with our binomial theorem. How are we going to do it? Let's find out. So I'm just going to let my function. So let's prove this. I'm going to let my function. I'm going to let f of x be equal to x plus y to the n. We're just going to let y be a constant. But in other words, we're just going to make it not be dependent on x. So what is the kth derivative of f of x? Funny you ask. So, what happens? Let's do the first case. So the first derivative has been great. Why aren't my calc students here at 3:35 in the morning? They got a test this week and they need to know how to do the chain rule. They would have really benefited from this. So, what happens? Well, you do a chain rule. What does the chain rule tell us? Well, we gotta take your inside and your outside, and we gotta do some derivative stuff to it. What is it? So your inside function here, you got this x plus y. What's the derivative of x plus y? It's 1. Trust me. And then what happens? Okay, so that's your inside. Your outside function, well, it's just, let's say u raised to the n. What's the derivative of that? As power rule, is n times that thing raised to the n minus 1. Perfect. What was that thing? It was x plus y. Awesome. Now, what happens when we take the second derivative? I'm so glad you asked. So we take the second derivative. Well, we already started here, and, well, we just sort of multiply this n, and we do another chain rule on this x plus y business. And we get n times n minus 1 times x plus y to the n minus 2. And so we see what's happening here is as we continuously take derivatives, we are going to get these falling factorials, these factorials of k many terms. So let's actually write that down. What's our general form? It's going to be n factorial divided by n minus k factorial times x plus y to the n minus k. Wonderful. So what are we even gonna do with that? I'm so glad you asked. Let's do it. So this is actually, in a sense, the thing we need, the thing we didn't really have at the beginning to solve this here. The other thing we need to do is, well, it's an infinite sum, this Maclaurin series, but luckily, once we get to f of what? We take n plus 1 derivatives of x. If we keep on taking the derivative of this function, luckily, we end up at 0. We cannot take the derivative after n many steps. Once we're at, say, plug an n into this guy right here, we have n factorial divided by n factorial times x plus y raised to the 0, or 1. This just turns into a constant. Derivative of a constant is 0, so there's only going to actually be n terms in our Maclaurin series. Perfect. So let's write it out. Okay, Maclaurin series, it's got n terms, and they are, I guess, let's use k here, because that's what I've been using. They're the kth derivative of our function at x. Oh, I guess maybe make this a little easier so I don't have to keep writing. Our function f of x was x plus y to the n. Perfect. And in particular, we're taking our function, our derivatives when x is 0, and we're going to multiply that by x to the k, divide that out by k factorial. So let's use this information we have. Well, we have our kth derivative of x being n factorial divided by n minus k factorial times this whole thing. So that at 0 is going to be the same constants, but x is 0, and we're left with this y to the n minus k. Sick. So what happens here? We get, let's see, sum from k equals 0 to n of n factorial times n minus k factorial times k factorial. Got this x to the k times y to the n minus k. Whew. N factorial divided by n minus k factorial times k factorial. That has the same count as n choose k. Oh my gosh, it's the binomial theorem. Clear as mud. Oh, what do we got? Oh yeah. Oh, there's caps missing. Yeah. Oh geez, there's so many caps missing. Sorry, I'm just here for some water. Okay, let's do, what, 1 or 2 more problems? Yeah, let's see. No, actually, maybe we'll do that, but I want to do this one, just in case we can't do any more. I want to at least do this problem. So, probably should have done this one before, because this is actually used in this problem here. But just in case you didn't believe me, we're going to actually use the binomial theorem to prove that the power rule works, which, don't get it twisted, yes, the logic doesn't quite make sense. if we started there to get here, can we use the binomial theorem to get this and then use that to get the binomial theorem? I don't know if that's really fair, but I don't know. I didn't write the rubric. I'm just the teacher. So what am I going to do here? Let's see. We're going to try and use the binomial theorem to prove this jazz about the power rule. So let's do it. I'm just going to grab one more pen. Oh, reliable. Okay, so I'm going to take this derivative. We're going to take the derivative. I'm going to take the derivative of x to the n. And now, just by definition, that's the limit as h goes to 0 of x to the, that's x plus h to the n minus x to the n divided by h. Okay. Okay, no, we're good. Okay, so we want to use the binomial theorem here. Lucky for us, there's a binomial here. So it seems like if we just follow our nose, hopefully everything will work out. So let's expand this x plus y to the n using the binomial theorem and see where we end up. Okay, so what do we get here? We have term 0 to n, and choose k, and now we have x to the, x to the k, h to the n minus k, and then let's just make sure we grab everything else here. Okay, wonderful. All right, so let me see. What do I want to do here? Well, it would be really great, and anyone who's done derivatives before, it'd be really great if I can get rid of this h here. If I can get rid of this h, then I can take the limit of this, I can take the limit of this function, and I will end up, I guess, with something. That's great. So what that means is I want to get rid of this x to the n. I want this to go bye-bye. So let's see how can we make that happen. Let's write our limit there. Let's see if there is just an x to the n living among these terms here. Let's see. So if k is equal to n, what is the coefficient of x here? Let's see. So we have n choose n, which is 1, and we have h to the n minus n, which is just 1 as well. So it turns out the coefficient of x to the n in this binomial, in this polynomial, it's just 1. So let's rewrite this. This is the same as okay, here we are. This is the same as this sum. This is the same thing we had right here, just we pinched off the x to the n term, and we still have that 1 subtracting out here. Cool. And then still dividing by h. These guys are going to subtract, they're gone. And also a nice thing to think about here is that when we pinch off this x term, x to the n is the only term in this polynomial that doesn't have an h. Because let's sort of just look at all of our values of k. So we have k equals 0, h is raised to the n, all the way up to k equals n minus 1. We have h to the n minus 1, or h to the 1. So we have an h in there. So that's great. So we can actually, again, just sort of with this idea of like plucking things out of our sum, we have at least one h in every term here. So I'm just gonna just sort of distribute that out of our sum. Okay, what is that gonna look like? K equals 0, still to n minus 1. Now n choose k, x to the k times h to the n minus k minus 1 divided by h. Perfect. So now these h's are going to cancel. And so we can just take the limit. Take the limit as h goes to 0. And everything that still has an h here is just going to go to 0. And we're just left with only the terms when h is sort of missing. And which term is that? Well, let me rewrite this actually, so to make this a little bit clearer. This is n minus 1 minus k. Sort of write it like that. Cool. So written like this, if we plug n minus 1 into our value of k here, we get h raised to the n minus 1 minus n minus 1, or just 0. So we get the n minus 1 term, or choose n minus 1 times x to the n minus 1. And what is n choose n minus 1?
N choose 1.
And what is n choose 1?
N.
Very good. Perfect. And we end up with the derivative of x to the n. I find that problem so cute. So, yeah, I think it's a very fun one. And then, I've spoiled it.
Just for a second.
Just for a second, for those astute viewers. Okay, I'm gonna roll with it. I like this problem. We're gonna do it. We're gonna finish off by one more, trying to find the binomial theorem, and we're gonna flip a biased coin. So we got some probability up in this. So let's see. I'm gonna erase all of this. So if I am flipping a coin, I'm gonna flip it, say n times. And I'm gonna work with a biased coin. I'm gonna write down a few things. I keep on erasing you. Okay. So let's actually make myself bigger. So we're going to work with a biased coin. What does that mean? Well, if I'm working with a regular coin, that's just, 50-50 odds. 50, like, half of the time I'm gonna get heads, half the time I'm gonna get tails. We're going to just let P be the probability of heads. And with probabilities, we only ever allow probabilities to go between 0 and 1. So the probability of heads is going to be 1 minus P. That is to get tails. Okay. Yes, so if the probability to get heads is P, then the probability to get tails is 1 minus P. Okay. So if I say I flip a coin n times, what's the probability that I get k heads?
Exactly, or?
Exactly k heads, yes. What do we think, everybody? Let's think about it maybe in one way. So say my ordered matter. Let's say I get heads in the first k things, and then I get heads the rest of the time. Okay.
Sorry, tails?
Sorry. Thank you. I keep saying heads, so apologies. Yes.
The two sides are both heads.
Are they what?
It's, one of them two-faced coins.
Oh.
You make your own luck.
Very nice. Yes, it is one of those two-headed coins. One's got them scratches on it. Batman saved me when he could have saved my woman. It could have been me. Anyway, so so the probability every time I flip the coin. There's a P probability that I'm going to get heads, and there's 1 minus P probability I'm going to get tails. And if I get heads k times, we get it in P to the k, and that means I got tails in n minus k. But wait, what's that?
Order matters.
Order mattered when for a second, but orders shouldn't matter because it only mattered that I got k heads at some point. So if I did n trials, I can choose any k of those to be heads. Well, I can't choose it, but that'll give us all of the possibilities rather. If we get exactly k heads, then it had to have been from k flips of the n total. So that's if I wanted exactly k. Say I want any possible k. Well, we will just sum that up. We'll sum it from all possible values. So I'm doing n trials of flipping a coin. If I can get no heads at all. That is a possibility. Or somehow I got n heads. And I can get anything in between. And that's all there is. So what's nice about that is with probability, this sort of, and I'm just going to sort of wave my hands here, but in a mathematical sense, this is telling us all of the possible ways that this event can happen. So we can think about this as like, what's the probability of anything happening? So the answer is 1. If and that just means that if I flip a biased coin n times, then I got some ordering, then k of those were heads, and they came in some ordering. That's definitely going to happen. So this is just sort of a given. Now, we're very close. This looks like binomial theorem, almost. So what else do we have to do here? Well, I am just going to substitute. Why not? We're going to basically just pick a nice value of p. We're going to set p equal to, and I think in this particular problem, yes, in this particular problem, going back to your question a while back, we we force x and y to be positive. Yes, we need x and y to be positive. And I'm just going to set p to x divided by x plus y. And just for a sanity check, the idea with probabilities is that they are less than 1, and x divided by x plus y, if x and y are both positive, then x is less than the sum, so it's less than 1. We're chilling. Okay, so let's plug this in to our formula here and see what we actually end up with. Okay, P is this whole shindig. Oh, this is perfect timing. Okay, x divided by x plus y to the k, and we get 1 minus x over x plus y to the n minus k. Okay. This, turns out, is just going to be y over x plus y. We can also think of that just as what would I need to add to x over x plus y to get 1, for instance. It would be the complement probability. Anyway, this whole thing is equal to 1 still. So what do we get here? Let me actually just, for sake of time, I'm just going to write that here. Y over x plus y. Okay. So this has y divided by x plus y, and we have x divided by x plus y. So I'm just going to sort of distribute this x plus y business out of here. And let's see what we actually end up with. So this x is divided by x plus y, and there's k of them. So we get x plus y to the k from here. And then from this one, we get x plus y to the n minus k. So multiplying those together, we're going to get 1 over x plus y, 1 over x plus y to the n. And then that's multiplied by x to k and y to the n minus k. Whew, all right. Now, what's the last thing we get to do here? I guess it's sort of a concept that we haven't discussed. No, I guess that's totally fine. Anyway, x plus y to the n. So as it was written above, we were made to think that all of this was dependent on k, but there's no k floating around here, so I can just multiply both sides by x plus y to the n, and just get rid of this term. I can just pull it out and then get rid of it. Trust me, please. And if we sort of get rid of all of the scratch there, we see we actually end up with what we were looking for to begin with. Maybe it was contrived, maybe it was confused, but it is true. Okay, I think that will do it. Thank you all for tuning into this. Get ready for the last quarter. I mean, we're gonna go for a small break right now, though. So I'm gonna